So let's look at this problem now, threesome. In this problem, we are asked to return three numbers whose sum is equal to 0, and we need to return all such triplets, provided that we should not return duplicate triplets. Okay. So now one thing, first let's discuss the brute force solution. Brute force solution would be quite simple. We will just have three loops, one for each number, and at the end we will see if they add up to 0. If they add up to 0, we can store the result in a set to avoid duplicates, and then later we can convert that set into a vector, copy that basically. So why did I use set? Whenever I see something like duplicates should not contain duplicates or involving duplicate keyword, my first thought is to think about set. Alright, so I won't code it up. Let's think of a better solution. In previous problem, we were learning about two pointers. Two pointers has one condition. The array should be sorted beforehand. So let's say that if we sort this nums vector, then what we can do is we can fix a number first as our first number in the triplet, and then in order to find the other two numbers of the triplets such that it add up to 0, we can use a two-sum technique. Let me code it up and explain it side by side for better understanding. Alright, so first step is to sort this. So let me write nums.begin, nums.end, and the length of my vector is n. Alright, so what I want to do is my I is initially 0 and I'm running till n minus 2 because I'm putting I as the first number of the triplet if possible. Okay, now I have this number. Let's say that I have fixed my nums of I as one of the numbers in my triplet. So now I need to find two numbers such that their target is equal to minus of nums of I. Let's say that because we want to find number our target as 0, let's have two pointers left which will be pointing to the I plus 1th index, and another one right which will be pointing to n minus 1. Okay, now simple two pointer technique, that same template. While my left is less than right, what I do is I calculate my current sum. So my current value is nothing but my nums of I plus nums of left plus nums of right. Okay, so typo here, plus nums of left. Okay, now if my current value is exactly equal to my target, which is 0, then I know for sure that such a triplet will be a part of my answer vector. But I also need to consider the duplicates part. So let me first make a set of vectors, because there will be three numbers in my vector for the set. Let's name it as t. And what I can do here is that I can have st.insert and the three numbers, nums of I, nums of left, and nums of right. Okay, now we have done that, and now we need to find a next triplet. Okay, so for that I have to move both my left and right pointers. Why both? Because let's say that the numbers, my left and right pointers were exactly 1 and -1, let's say. So the sum was equal to 0. Now if I'm increasing only my left pointer, if my left pointer, let's say, is pointing to -1 and my right pointer is pointing to 1, and let's say if I'm only increasing my left pointer, so my -1 will be definitely increased to some value, let's say 0. But then we won't find the triplet, right? So we will have to move our right pointer as well in order to have the possibility of finding another triplet. Okay. What will be another condition? Another condition would be that if my current value is less than target. If it is less, then it means that I need to increase my current value. And the way to increase my current value is to increase the left pointer because the array is already sorted. And the last case is my right pointer, given that my current value is greater than target. So I have written all the three cases. Now there is one more thing remaining. Let's declare my answer vector somewhere at the top because we will be later optimizing it further. So let's say my vector of int answer is my answer vector from which I want the results. And what we can do is we just have to copy every element of my set in this vector. So I can write something like answer dot push back of my IT, and then let's return this answer. Let's see run if it runs fine or not. Okay, we are getting our sample test cases pass. Let's discuss the time complexity before submitting it. Okay, first we are sorting the array, so that means our time complexity is n log n for sort operation, right? Then what else are we doing? After that we are traversing here up till n, and in this traversal we are also traversing to our left and right pointers. So this while loop will run n times for each I. So basically this is a n squared loop over here, and set insert will take another log of n operations. So log of the number of entries in my set data structures, it will take another log n. So this will be my n square and log n. Okay, what are our constraints here? Constraints goes from 3 into 10 raised to 3. So this number will be roughly equal to 10 raised to 6 and then log n extra. So and also n for this last copying part. So let's see if this solution gets passed or not. Okay, we are getting it passed, but our runtime is very high. We can optimize it. How can we optimize it? Over here, in order to consider the duplicate element, what I am doing is I am checking again. I am going through my while loop again and again, even if the values are duplicate. So these extra n's are causing me a lot of time. So let's say that our initial input was something like 0, 0, 0, and then 1, 1, 1. This I am writing after sorting it. Something like this. Okay. So what it means is that for every -1, firstly I am going and writing my left pointer at this point and my right pointer at this and doing the computation, finding that okay, this -1, 0 and 1 is basically pointing, or -1, 2 pointing. So I am basically checking for every such element, thus increasing my complexity. If I know that I am fixing a number which is -1, I have fixed it once, then whatever my I pointer, let's say, when it reaches this -1 again, then I would say, but didn't we just do it already? We already had the answer in which we have fixed our -1. Then why are we fixing -1 again? So in order to deal with this, what we can do is that we can have a check. We can have a check such that while my nums of I is exactly equal to nums of I minus 1, then I increase my I pointer, because I don't want to fix my -1 again. I don't want to repeat it. And in order for this condition to be true, our I should be greater than 0. Okay? Because it's I minus 1 here. So I only should be greater than 0. Okay, so we have done some optimization here. Now let's do another optimization. Isn't this the same thing when we are, let's say that I have fixed my I as -1 here, and my L up to a point reached 0. Okay, let's say my R was here, but that is not important. Let's say my L was here. I have fixed my -1 for I and 0 for L. Then if I am following the structures, my L will again reach to this 0 and then try to find the same R. But that's unnecessary because I don't need it. I don't want to have duplicates again. So what I can do is, if my L value is also repeating, I will be moving it forward. Okay. So what this means is that instead of just writing left plus plus in this, what we can do is we can have the exact same thing for my left pointer. So if my left is while my left is less than right, and nums of left is exactly equal to nums of left minus 1, then I do left plus plus here. Alright, and the same thing I can do for right as well. For right as well. Right plus 1 and right minus minus. Does that make sense? Okay, one last thing. We don't need now this set at all. We can directly push our answer in this answer because we are already dealing with our duplicates part. Okay, so we don't need this as well. Let's see and run it, and then we discuss its time and space complexity. Okay, so somewhere we are leaking memory. Let's see where. Okay, so at first I have sorted this n minus 2 while I is greater than my 0, and I am doing this part. Okay, this runs fine. Okay, everything is fine till here. So what am I missing here? We are not considering, we are moving the i's as required, since if my nums of I is exactly equal to nums of I minus 1, I don't need those values, so I just move them apart. Alright, okay, that thing is already fine. Okay, let's see, we don't need this value here. And before moving here, what we need to do is we will do left plus plus. Let's see if it runs here, because in order just to avoid some things. Okay, so now we are passing. Great. So the problem was basically that I was checking my left and left minus 1, which were not equal to true, which were not equal, because I hadn't increased my left initially, and I was comparing with a previous value which was supposed to be different. So let's discuss the time complexity of this solution. Over here, what we did, we improved. First of all, we just have this n loop, and for each we are doing this part, which would optimize a lot because we won't be going inside this. But for the ones in which we go inside, this will also run only n times. So in total, this whole operation will be n square, and n log n for the sorting, plus n square. Okay, and for the space, we are not using anything extra. Before we were using a set, so that was increasing our time complexity by O of n. Let's submit. Okay, something is off here. Let's write a if condition instead of this, because our I is already increasing by 1, and let's just don't go further. Okay. Okay, perfect.